There's a tiny piece of code running on your laptop and on nearly every server you touch today. Its whole job is to estimate a number that keeps changing using almost no memory and almost no compute. It is TCP's retransmission timer, and its core has not changed since 1988. It keeps two running averages with weights chosen so that every update is a simple bit operation, no multiplier. It's well engineered, but it's also just using a rule of thumb, and it has needed patch after patch ever since 1988. But I'm not here to talk about networking. TCP is just the most familiar version of a problem that is everywhere, tracking a changing probability cheaply, right where the data is. The real question is how small a complete learner can be, and whether we can put real intelligence into the smallest devices we build. Not a quirky bit trick, a learning element for AI at the endpoint. Today I will show you that element and why it works. A quick word about the International Symposium on Computer Architecture, since this is our third year at the workshops. 2 years ago, we introduced the device and the procedure it runs, called the Cincinnati Algorithm. Last year, we composed many of them into a system that discovers relationships with no matrix multiplication. And I argued last year that learning is really compression in the Claude Shannon sense. A learner earns its keep by squeezing the surprise out of a stream. That framing is catching on. This year, we bring two new things: the math that proves why it works, and the first hardware. FPGA learning simulations and a proof of concept chip fabricated at TSMC, now in packaging and test. Here's the whole idea in one picture. A probability looks like a pie chart. Red is the chance the next bit is a 1, blue is the chance it's a 0, and there's a thin unfilled wedge, the part the device is still unsure about. The estimator's entire state is one integer, and that one number holds two things at once: the current estimate and how much evidence is behind it. Early on, the pie is coarse, the unsure wedge is wide. But as observations arrive, the pie splits into finer slices and the wedge narrows. Precision is not a setting you choose, it grows on its own. No counters, no running sums, no stored history, just the integer. So how does it learn? It makes the prediction and then it adjusts if the prediction was wrong. The prediction is like throwing a dart at the pie chart. The estimator compares a few random bits against its stored bits and it reads off a guess, a 1 or a 0. Guess right, there's nothing to adjust. Guess wrong, and it tweaks the model towards what it just saw. And here's where my own thinking had to change while designing this. A binary stream looks like a two-outcome world. Either the guess is right or the guess is wrong. Either you hold or you nudge. But a learner with only those two moves is stuck at whatever precision it started with. It needs a third move. Get more precise. The random bits are what open that third door. Pair every stored bit with a random bit, and once in a while the random bits match the stored bits perfectly, all the way down. That indicates that the dart landed in the wedge of uncertainty itself. That third outcome is a signal to grow in precision. The pie gains a bit and it gets finer. 3 outcomes from a stream that only ever says 1 or 0. And here's the part that matters for hardware. The dart is thrown before the observation arrives. The random draw, the comparison, the preparation of what to change, all off cycle while the model holds its prediction. Then the observation lands and the learning commits on that one clock tick. If it's the right guess, it holds. If it's the wrong guess, it nudges one slice towards the truth as a masked XOR. In a moment, I'll show you just how little hardware that takes. But that, in essence, is the Cincinnati algorithm. A prediction is prepared in advance, a third door is opened by randomness, and a correction that commits the instant the data arrives. And here is why an architect should believe the no arithmetic claim. Line up the wedges as bits. The biggest is half, then a quarter, then an eighth, each a stored bit, red for 1, blue for 0. Throwing a dart is just one scan. Compare a random bit to each stored bit, the biggest wedge first, and stop at the first disagreement. That predicts the wedge's color. That predicts the bit. You stop at the biggest wedge half the time, the next a quarter, exactly as the wedge sizes. In gates, a find the first difference, a priority encoder. And the correction is just as cheap. To nudge, start at the smallest wedge, find the first one whose color matches your prediction, and flip everything up to it, including that bit, with a single XOR operation. There's your plus or minus 1 with no adder, no carry chain. Prediction is one scan, correction, a priority encoder, and a single XOR. That's the whole learner. These are gates a student could draw on a napkin. If you lay out every state the estimator can be in and every move it can make, you get a Markov chain. Each state is one of those pie charts. Each observation pushes it up a slice or down a slice, or it grows it. Now, feed it a stream that is 80% ones. States that guess too low get pushed up. States that guess too high get pushed down. The mass piles on the few states that bracket the true ratio, and it stays there. Nobody told the estimator the answer was 80%. It discovered it one bit at a time, and it stays ready to move the moment the world changes. Here's the part I want you to take home. Hardware primitives almost never come with closed-form theory. This one does. When the pi reaches full width, the chain settles into a distribution we can write down exactly. It's a binomial. Not approximately, exactly. That hands us the mean, the variance, and the drift, all in closed form. And here's a remarkable part. Nobody chose the binomial. We chose the rule for hardware simplicity. Compare bits, flip bits, nothing else. But that rule makes the pull towards the truth a perfectly linear restoring force. And a chain with a linear restoring force has no choice about where it settles. The binomial was not designed in, it emerged. And this goes further. Compare the estimator's running estimate to classical Bayesian inference. At every observation count, it sits between two of the most principled rules in statistics. Jeffreys on one side, Bayes-Laplace on the other. Sandwiched between them, converging at 1 over t log 2. No prior, no likelihood, no posterior. So think back to how I started this video. This is the kind of estimator you have trusted in TCP since 1988, with exact statistics, nothing to tune, and not a single multiplication. That's the punchline of this whole talk. It took heavy mathematics to prove that the learner needs none. The math is heavy, so the hardware can be light. Simple bit manipulations go in, and exact principled statistics come out. But one estimator tracks one probability. The real question is whether they compose. Wire 3 of them together, and they discover the relationship between two data streams. In simulation, 3 composed estimators reach about half the error of 3 carefully tuned filters. And here's the part that matters in the field. When the distribution shifts, the tuned filters degrade by factors of 3 to 35 because their tuning was for the old world. But the estimator just keeps tracking. No retuning because there was nothing to tune. And nowhere in that update path is there a matrix multiplication. This is how you build a model by discovering relationships instead of brute force arithmetic. So we built it. On an FPGA, the 8-bit learner takes 48 lookup tables at 8 registers at 96 megahertz with no multiplier and no adder. And we have a proof of concept chip fabricated at TSMC, now in packaging and test. The energy story is not about gate count per learner. A stripped-down conventional filter can be small too. The point is what happens at scale. Conventional learning shuttles state back and forth to a central math unit, and at scale, that data movement is the cost that dominates. That dominates current AI, moving the data back and forth. The estimator computes right where the state lives. No math unit, no state crossing the die. This is what lets you put thousands of these on one chip. And that is the real goal, putting intelligence into endpoint devices, the sensors and small machines where learning is impossible today because the power and bandwidth are not there. TCP showed you the problem, tracking a drifting probability cheaply and in place. We built the element that solves it, and we proved why it works. Exact statistics from simple bit manipulations in a footprint small enough to put real learning everywhere. We think that this is the substrate the next era of AI gets built on, not just in the data center, out at the endpoint.